So in the last session, we discussed about gravitational force, then gravitational force per unit mass, right? So gravitational force we understood as G mm divided by r squared. Then gravitational force per unit mass, so that would be Fg divided by simple m, and that is Gm divided by r squared. So if you look into this, we simply cross multiplied. So Fg divided by m, this is called force per unit mass, right? So that is given as G. So this G means force per unit mass. Force per unit mass. So that is called gravitational field intensity as well. This is called gravitational field intensity. This is called gravitational field intensity. So this we discussed in our last session. Now, if you plot F versus R, if you plot F versus R, it looks like in this way. It looks like this. You understand how this truncus type of curves looks like, right? Now, if you want to discuss about gravitational field intensity, how that works, so that would be R versus G. That also has the same shape, similar shape, right? Truncus type shape. Now, we have to be very careful when we are properly drawing this because of the radius of the Earth, right? So now let's try to understand that. So suppose this is the Earth radius, R. This point is RE. This is R. This one is G. So what we are going to have here is we are going to have this guy. Why? Because of this inverse behavior. G is inversely proportional to R squared because of this behavior. Now, the G value on the Earth's surface is going to be 9.8, 9.81, right? So that is 9.81. And then you can see when you are deviating, it is decreasing. So for example, here, this can be 2RE. So at that point, your G value is much lesser than 9.81, right? So this is what we can observe, right? So we understood the related theory last time. Okay. Let's think about work now. Let's think about work. So, in VC physics, we don't have calculus, but we have to find physical properties accordingly. Okay. So, work. What is work? Work means work done, right? What is work? Work is equal to force times displacement. Work is equal to force times displacement. right? So this is like F times R now. F times R now, right? Actually, this is not the proper way of doing this. I don't know how many of you will understand this. Actual way of finding work, W, is integral f of dr. This f is a function of r. So those who have done calculus in the senior class, you probably know this. Now this piece we teach you in the calculus in math methods. So I will remind you when you are there. But unfortunately in physics we don't have it. Now when you are doing this, you can see this is the area under curve. This is area under curve, right? So this is area under FR. Okay. So now if you have a question like this is F, right? And it is going like this, right? Now this is when R is equal to RE. This is when R is equal to 3 RE. Okay, 3 RE. Now what is happening? Now this object is going to bring from the Earth's surface to a situation like this here. Correct? So in here. So when you are bringing this from surface to this point, the distance is what you can see. This distance is essentially 2RE now, yeah? Correct? That distance. So we have to do some work. Why? Because we are bringing that from here to there. Right? So that work, this work, how to calculate? Now, if you really want to calculate this one, you need calculus. But in the exam, what you have to do is, the exam people will give you the same exact diagram. What you have to do, you have to find this area. You have to find this area, right? This area is equal to work done. When moving this mass from A to B, right? Work done on mass what? Mass M. Mass M. Why? Why it is mass M? Because this is Fg. Because it is Fg. Fg is defined as GMM divided by R square. So what you are bringing from A to B is that simple M mass. Should be clear. So now how do you find this area? You can't use integration in calculus. What you have to do, very simple thing, you have to count the number of squares. 1, 2, 3, maybe this is half, maybe this is 1, maybe this is 1. Full squares you count, and then you estimate this. Maybe half, maybe 1/4, maybe half, like that. So you give an estimate. Correct? So now, how do you know the area of a square? It is given to you in the exam. They will give you this is in meters, this is in newtons or whatever. Then you will know from the diagram the size of this block or the side of this square is 1 meter. This is 1 meter. Right? Or this is 10 to the power 3 meters. Or this is 10 to the power 3 meters. This is 10 to the power 6 meters. So you will know. So that means this side length you will know 10 to the power 6 meters, something like that. So then you know precisely how much is this, how much is the area, right? So what you have to do, you count the number of squares here and then get estimate. Suppose there are 9 squares. Now one of this is 10 to the power 6 and this is 10 to the power 6, yeah? So 9 multiplied with 10 to the power 12, right? That's the area. That's how you do it, right? Very simple. Now, so this is easy. Now again, I'm telling you this mass, again I'm telling you this mass is simple M mass. That mass is going from A to B, right? Let's talk about what is happening with unit mass now, right? Work done for unit mass. Work done for unit mass. So in that, your plot looks like this, but this is R versus G. R versus G. So you are going to bring that from this point to this point, for example. So this is RE. From here to here, in general, it's going to be R, for example. So RE is the radius of the Earth, right? So now you are looking at this point and the corresponding point to this simple R, which is this, right? Now understand what this area gives you. Understand what this area gives you, right? Understand what this area gives you. This area is equal to, right, work done on unit mass. Unit mass means 1 kilogram. When it is bringing from when it is bringing from I would say this is A, this is B, A to B, right? Now, again, I'm emphasizing you this unit mass thing. Why I'm using unit mass concept? Because I'm looking at G in the diagram. G is force per unit mass, correct? Force per unit mass. Let's think about a question now. Simple question, right? Uh, Consider the following sketch. Or consider the following diagram. Okay, this is just to understand the concept. So this is a point, Earth's surface, and we are bringing that to this point, B point, right? So this is RE. From here to here, it is going to be 4 RE. RE is from here to here. So this value is 9.8. Okay. This value is 9.8. Right. And then this box here, length of this is going to be 10 to the power 4 meters. Actually, let's hold on. Just say this is R, okay? So 10 to the power 4 meters, right? So this is R versus G curve, right? Question is this. Find the work done on mass M is equal to 10 kg when it is transported from A to B. Okay. We'll carefully do this one. So when you do this question, first of all, you have to look into this. So that means this curve is drawn for unit mass, 1 kg. So how many boxes are there now? 1, 2, 3, 4, say 5, 6, 7, 8, 9, 10, 11, 12, 13. Roughly 13. Yeah. So 13 boxes multiplied with how much is the area now? 10 to the power 8. 10 to the power 8. Right? So that is for work done. This is work done, obviously in joules. Work done in joules for 1 kilogram. So now you have 10 kilograms, right? So it's just a matter of you multiply that by 10. Right? So total work is 10 times, that's the mass. This number, 13 times 10 to the power 8 joules. So that sounds good. That's how you do that. Satellite motion. Right? So what we are going to understand here is this. This is the orbit. Orbit. So this is R, Earth radius. You can say RO, RE, doesn't matter, right? So from here to here, simple R. Simple R. This mass is capital M. The mass of this satellite is simple M. Right? Now what we do, when you place a satellite on the orbit, we give an initial push. Initial speed is provided. How do you do that? When you put this satellite on the orbit by using a rocket, for that satellite, the initial push is given. Initial push is given. right? And that due to that, it gets v speed or v velocity speed, right? Now this is perpendicular to that line, right? Now, if you think about the physics, you can see this mass is going to have a speed which is perpendicular to this radius, right? That means it goes in a circular motion. So it goes in a circular motion. So if it goes in a circular motion, there should be a force towards the center. There should be a force towards the center, and that force is called centripetal force, right? Fc is nothing but centripetal force. Fc is nothing but centripetal force, right? Why this object has a centripetal force? Because it goes in a circular motion, right? Now, if it has a centripetal force, it should have a centripetal acceleration, right? So in this direction, it should have a centripetal acceleration. We usually denote that as AR, right? We know that in circular motion, we call it centripetal acceleration. We call it centripetal acceleration. Or we call it radial acceleration. So we usually put R to say radial because it is towards the radius. We call it radial acceleration. Right. So radial acceleration is defined as v squared divided by r. Radial acceleration is defined by v squared divided by r. Correct. Now what we do, we try to use F is equal to ma. So now this is a circular motion question. F is equal to ma is used where? Towards the center. F is equal to ma is used towards the center. Agree? Now, what would be the F here? What would be the F here? This centripetal force. Now, this centripetal force in this case is going to be the gravitational force. So, in this case, centripetal force is gmm divided by r square. Now, this is the connection between circular motion and this situation, right? The force value is different in this case. Why? Because it's in a gravitational field. Right? I hope you understand that. Now, I'm going to use F is equal to ma2 as a center, and that F is going to be gmm divided by r square is equal to MAR. MAR. Right? Now, I'm going to do the substitution for AR, which is going to be M V squared divided by R now. Is going to be gmm divided by r squared. Now, I would say this is my second equation, but I can still simplify this one. Now look what I'm doing. I'm going to cancel m and m here. I'm going to cancel m and m here. And then r and r here. Then what I have here is v squared is gm divided by r. V squared is equal to gm divided by r. Okay. Now, I'm going to find v now, taking the square root of this one. That would be gm divided by r. Gm divided by R. Okay. Okay. So now here you can see this V is simple M independent. This V is simple M independent. Why? Because of that cancellation you can see in equation number 2. Right? So that means if you keep a satellite here, if you place a big elephant here, if you place a car here, doesn't matter what object, what size you keep there, the speed is going to be the same. Speed is going to be the same. You put a small ant here, right? Speed is going to be the same. Why? This is exam question. Why? Because this V is M independent. You can see that cancellation. See? So if you have elephant here, elephant gone. You can see ant gone in this calculation. So that is very important. Okay. Right. Okay. So that I hope you understood. Right. Now, right. Special note here. We understand G is equal to Gm divided by R squared, right? We understand Gm is equal to Gm divided by R squared is equal to G. What is that? Gravitational field intensity. Indeed, this G is R dependent. So this is our equation number 1. Now here, in this situation, satellite situation, we got V is Gm divided by R. Okay. Now look at the math. This V also R dependent. This V also R dependent. Yeah. So this V R dependent and M independent. R dependent and M independent. Right? So this is our second equation. Now, what you can do, you can find a substitution. You can find a substitution here. What that substitution is this. GM, right? So from here, I'm going to get V of R is equal to Gm is G of R square. Agree? And the R in the denominator, I'm going to copy. Agree? Right? So from here, you get this to be GR square root. GR square root. Now, you can see this G also R dependent. This G also R dependent. And you multiply it with the R at that situation. Right? You understand what I'm saying? So this G is nothing but at R is equal to R. Right? So this calculation is very important for you to understand. There is no point memorizing it. You can't memorize math. So what we understood this. Now, let's try to understand this more. So we are going to have a mass here. I would say M1, and this is V1. And I'm going to have another orbit here, which is R2 here, and that would be V2, right? So this is M2. Okay. So now you can see that V is equal to Gm over R, right? So you can write here V1 is equal to Gm divided by R1, and V2 is equal to Gm over R2, right? So you will understand now this and this are constant speeds for that orbit. Why it is constant? Because G is a constant, M is a constant, R is a constant. What is M here? M is the mass of the Earth here, M. Okay, so V2 also a constant, right? So you can see from here, V1, comma V2 are constants. V1, comma V2 are constants. Okay. Now let's try to find out V1, V2 in terms of the other formulation, right? So V1 is equal to G R1, and V2 is equal to G R2. What do you think about these two equations? What do you think about these two equations? Actually, if you really look into this, if you really look into this construction, right? Wrong. This is wrong. Why it is wrong? Who can tell me? It is wrong because of this G. It is wrong because of that. Because you have to understand, G is the intensity for the orbit, right? So G means the force per unit mass. So this is G. And the force per unit mass for that other orbit is G according to my calculation here. How come that is possible? How come the same G is possible for two orbits? What is G? Force per unit mass. So when you put 1 kilogram here, the force is G. When you put 1 kilogram here, then again the force is G. How come this G is equal to this G? Because we understood G is R dependent. Ne? So if this is G, this should be G1 or something. So if this is G1, this should be G2. So you can write this V1 to be G1R1, comma V2 to be G2R2. Reason G is R dependent. Next subtopic is period of a satellite motion. Period of a satellite motion. What do you mean by period? What do you mean by period? If you think about a satellite motion, what do you mean by period? Time per revolution. Time for one round, right? Time per revolution. So period is time per revolution, right? So how do you find that? Time per revolution. Revolution means how much is the distance? 2 pi r. Second, 2 pi r. So you can do this. Period means time. You can take time from distance divided by speed formula. Or speed is equal to distance divided by time. That grade 7 math part. Right? Distance divided by speed. Now what is the distance in this case? 2 pi r. What would be the speed? The speed is v. So period is given to you by t, right? T is a period. And that is 2 pi r divided by v. Now, period is 2 pi r divided by v. Correct? Now we will play with a little bit of math. We know that v square is equal to gm divided by r. V square is equal to gm divided by r. How come? Here. Here. From there we got v square rooting. Right? Square rooting. So gm divided by r. So if you don't like that, I can simply say v is equal to gm divided by r square root. Okay? Agree with me? Now, you can see this v here and v here. You can see direct substitution now. Right? So let's do that. So t is equal to 2 pi r divided by, this is going to be gm divided by r square root. Right? So this is by substitution. This is by substitution. Okay. Now, because of the square root, now come to the math class. Because of the square root now, what we do? We are going to square both sides, right? So what we are going to do? So we are going to square both sides. So that's going to be t squared now. Right hand side you have 4 pi squared r squared divided by gm divided by r when you square both sides. Right? Now, you simplify this a little bit. T square is equal to 4 pi squared r to the power 3 divided by gm. Right? So you know how to play with the fraction division. Right? So I bring r to the top. So it's going to be r to the power 3. Gm stays in the denominator. Right? Now I'm going to pay attention. Now I'm going to pay attention to this block here. I'm going to pay attention to this block. Can you see that this block is a constant? Can you see that block is a constant? 4 is a constant, pi is a constant, g is a constant, capital M is a constant. What is capital M in this case? Mass of the earth. Mass of the earth is a constant. Capital M always we refer to the mass of the earth. Right? So it's a constant. So you can say K if you want. K if you want. Right? So writing t squared in this way. We wrote t squared in this way. If you want from here, you can find t, right? You can find t. That's not a big deal. That's the period, right? Now, this relation, is called Kepler's law. This relation is called Kepler's law. Or sometimes you can say t squared is proportional to r to the power 3. Kepler's law. Now, for example, if someone wants to find t, right? So if you want to find t, so finding t, so that would be 4 pi squared divided by gm r to the power 3 and the square of that one. Right? So that way you can find t if you want. But Kepler's law is the relation I showed you. Okay? Application. Simple application. Very simple. The question is this. There is an orbit and there is another orbit. Right? So the mass is here. So this is m, mass of the Earth. Now, from here to here, distance is r, right? And the period for this m mass is, this is v here, right? So the period is going to be t, period is going to be t. Now, from here to here, the radius is 3r, same mass, m, right? With a different speed, right? What would be T1, right? So write the period T1 in terms of T. Okay, very easy. We know that T is proportional to T squared is proportional to R to the power 3. Kepler's law, we don't have to write that constant, right? This is our first equation. If you think about the second one, that's going to be T1 squared should be proportional to 3R to the power 3. 3R to the power 3. Why? Because that's a radius, right? Now, if you want to compare these two, you can divide. Inequalities, if you divide, that becomes an equality, right? So what I'm saying is, when you divide 2 by 1, that's going to be T1 squared divided by T squared equal. Inequality becomes equality. So it's going to be 27, I think, R to the power 3 divided by R to the power 3. Agree? Yeah. So now R3 gone. R3 gone. So what you are going to get is T1 squared is equal to 27 T squared. So T1 is going to be 27 square root T. 27 square root T. Right? So that's the answer. So this will tell you that T1 is greater than T. T1 is greater than T. It is true indeed. Why? Because T is the time for one revolution on this orbit. T1 is this. T1 is bigger. So T1 should be bigger. That makes sense. Right? So somehow we got this relation using our Kepler's law. So this is the Kepler's relation. This is how we use Kepler's relation. So this mathematical part is a everyday thing when it comes to the exam question, right? So same exact thing you have to do in the exam. Details can be different. For example, you might get 2R, not 3R. That's it, right? So this is the end of gravitational field for BCE.